Hi viewers.
In the previous class, we obtained an expression for temperature difference in a lump heat capacity analysis as theta is equal to theta I into e raised to minus HAT by rho VCP. So this HAT by rho VCP you can rearrange in this form by taking the area into the denominator. So you get HT by rho V by A. V by A, volume divided by surface area, can be represented as characteristic length of the body. So you get the HAT by rho VCP as HT by rho LCP, where L is the characteristic length and which is given by volume divided by area. Now I introduced LK in the numerator and denominator. Same HT by rho LCP. So I just introduced LK in the numerator and denominator. So we are getting two factors here, HL by K and KT by rho L square, L into L square, rho L square Cp. So HL by K is there, KT by rho L square Cp. So that is written here, HL by K, KT by rho L square Cp. Now HL by K I will retain here, and K by rho Cp, which is thermal diffusivity. So it is thermal conductivity divided by rho Cp, density into specific heat, which is a thermal capacity. This product rho Cp is thermal capacity. So thermal conductivity divided by thermal capacity, that is K by rho Cp, is known as thermal diffusivity. So thermal diffusivity into T by L square. And we have studied in the previous class HL by K as a Biot number and alpha T by L square as Fourier number. So you are getting HAT by rho VCP as Biot number into Fourier number. So you can represent HAT by rho VCP as a product of Biot number into Fourier number. So the temperature difference equation can also be written in this form: theta is equal to theta I into e raised to minus Biot number into Fourier number. Instead of HAT by rho VCP, you can also write as a product of Biot number into Fourier number. Now, all of you know that temperature difference is varying exponentially because the equation indicates that exponential variation. So it can be exponential decrease in temperature or exponential increase in temperature. So in case of material is cooled, that will be exponential decrease in temperature. If the body is getting heated up due to the surrounding, it will be an exponential increase in temperature. So in this cooling process, you can see that in the initial stages of cooling, the slope is more. So that means temperature gradient is more. So when the temperature gradient is more, the temperature difference also should be more. And as the temperature difference is more amount of heat flows out of the body. Rapid heat transfer will take place at the initial stages. More amount of heat flows out in a given time period. So at later stages, you can see that slope is decreasing and the curve will become flat, and this become almost horizontal. After an extended period of time, the curve will become horizontal. That indicates that the process has reached steady state. The system has reached a steady state. So any system, as I mentioned earlier, if you leave for a longer period of time, it will attain steady state. So this is how the temperature varies with respect to time for a lump heat analysis. This is again heating of a material when it is subjected to unsteady state heat transfer. So the body temperature is less and the ambient is at a higher temperature, and the material gains heat. The body receives heat from the ambient or surrounding and gets heated up, and this is also exponential variation, exponential increase in temperature. And initially you can see the slope is more. That means the body receives more amount of heat in the initial stages, and as the temperature of the body rises, the heat transfer will decrease and the amount of heat received per unit time, it will go on decreasing, and finally it will attain the ambient temperature or surrounding temperature, and this curve will become horizontal. No more heat will be added to the or flowing into the body, and the system will reach steady state. Now we will see that characteristic length used in lumped heat capacity analysis. The different geometrical shapes I have shown here. One is a flat plate and another cylinder and a sphere. So we have earlier seen that characteristic length is given by volume divided by surface area. So for these geometrical shapes you can find out the volume, find out the surface area and substitute, which will give the characteristic length. All of you know that volume of this flat plate is one side area multiplied by thickness. So one side area, if I take it as A, this shaded area, if I take it as A into thickness will give the volume. And so total surface area is 2 times A, because other side also similar shaded portion will be there. So 2A is going to be the total surface area, neglecting this end area. So A cancels and you get thickness by 2. So characteristic length for a plate is thickness. This is thickness. So thickness, whatever thickness is there, half of that is the characteristic length. Now for a cylinder, the volume is pi r square, the end surface area, multiplied by L, the length of the cylinder. So pi r square L is the volume, and shaded area, that is surface area, is 2 pi r, that is perimeter, into length. That will give this shaded area. Again, you are not taking the end surface area, only this lateral surface area is taken. So that will is 2 pi rl. So pi rl cancels and you get r by 2. So that is the characteristic length for a cylinder. And for a sphere, the volume is 4 by 3 pi r cube and surface area is 4 pi r square. So 4 pi r square cancels. You will get 1 r here and divided by 3. So r by 3. So we have seen that characteristic length for a plate is given by thickness by 2, and for a cylinder it is radius by 2, and for a sphere it is radius by 3. Now we will work out an example problem. An aluminum plate with the thermal conductivity 160 watts per meter Kelvin, density 2790 kg per meter cube, specific heat 0.88 kJ per kilogram Kelvin, and with a thickness of 8 mm, is initially at a temperature of 640 degrees centigrade and is suddenly exposed to an ambient condition at 25 degrees centigrade. The heat transfer coefficient is 110 watts per meter square Kelvin, and you need to find out the time required for the plate to attain a temperature of 420 degrees centigrade. So these are the data given. Initial temperature of the plate is 640 degrees centigrade, surrounding temperature is 25 degrees centigrade. You need to find out the time required to attain a temperature of 420 degrees centigrade. Thermal conductivity and heat transfer coefficients are given. Density, thickness, specific heat is 0.88 kilojoule per kilogram Kelvin. So I converted into joules per kilogram Kelvin by multiplying by 1000. Now we know that the initial temperature and ambient temperature, and also we know the temperature at the end of a time period. So we need to find out the time to attain this temperature. So you know theta, this T minus Ta is theta and Ti minus Ta is theta I. So temperature difference is known, we need to find out the time. So theta and theta I are known. Theta I is 640 minus 25, which is 615, and theta is 420 minus 25 or 395. So characteristic length of the plate we need to find out. That is, for a plate it is thickness by 2. Thickness is 8 mm, so you get 4 mm, and 4 mm is 0.004 meter. And before proceeding with the lumped heat analysis, we need to check the Biot number. Biot number is HL by K. H is 110 watts per meter square Kelvin, and L is 0.004 meter characteristic length divided by thermal conductivity 160 watts per meter Kelvin. So substituting, we will get 0.00275, which is less than 0.1, which is the criteria for using lumped heat analysis. It should be less than 0.1. So since it is less than 0.1, the Biot number is less than 0.1, you can use lumped heat analysis. Now you can find out the temperature difference. 420, to attain a temperature of 420, we need to find out the time. So 420 temperature minus ambient temperature is 25, we will get 395 as theta, and initial temperature difference is Ti minus Ti, we get 615. Now you can use formula which you have derived earlier, theta by theta is e raised to minus hat by rho VCP. So now you can again take that area into the denominator of this equation. So if you divide V by A, that will give characteristic length. Okay. So you can write it as e raised to minus ht by rho LCP, because already we obtained characteristic length as 0.004. So instead of substituting the area, surface area and volume, you can use that V by A, the knowledge of V by A as characteristic length, we can substitute and simplify the equation. So theta by theta is e raised to minus ht by rho LCP. So theta we have calculated 395, theta is 615, and h is known, rho density is known, characteristic length is 0.004, and Cp value 880 joules per kilogram Kelvin. So by solving this, you get the time as 39.528 seconds. So it requires 39.528 seconds to reach a temperature of 420 degrees centigrade. That means from 640 degrees centigrade to 420 degrees centigrade, body takes 39.528 seconds to cool to that 420 degrees centigrade temperature. We will see another example. An aluminium sphere weighing 5.5 kg and initially at a temperature of 290 degrees centigrade is suddenly immersed into a fluid at 15 degrees centigrade. The convective heat transfer coefficient is 45 watts per meter square Kelvin. You need to determine the time required to cool it to 95 degrees centigrade using lumped heat capacity analysis. The properties of aluminium is given as K is equal to 205 watts per meter Kelvin, density is 2700 kilogram per meter cube, and CPS 900 joules per kilogram Kelvin. Now the data given is thermal conductivity 205 watts per meter Kelvin, heat transfer coefficient 45 watts per meter square Kelvin, density 2700 kilogram per meter cube, mass 5.5 kg, and specific heat of the material 900 joules per kilogram Kelvin. Now to find out the radius, we know the mass, and we know that mass is equal to density into volume. Mass is known, density is known, and volume of a sphere we know it is 4 by 3 pi r cube. So substituting for mass and density, you will get the radius of the sphere. So radius of the sphere is 0.07863 meter. So in this, the radius is not directly given, but they are given the mass of the sphere. So knowing the density of the material, we can calculate the radius of the sphere. Now the characteristic length of a sphere is given by radius by 3. So radius is already calculated. We will get the characteristic length as 0.02621 meter. Now Biot number is HL by K, substituting for the characteristic length, and heat transfer coefficient is already known, 45, thermal conductivity is 205. So we get the Biot number as 0.005753, which is less than 0.1. So lumped heat analysis is applicable for this problem, and it is not mandatory that you need to check the Biot number in this particular example, because they asked us to calculate the time using lumped heat capacity analysis. It's already mentioned in the problem to use lumped heat analysis. That means Biot number is less than 0.1. So but we wanted to ensure that Biot number is less than 0.1. So we got it less than 0.1. So lumped heat capacity analysis is applicable for this problem. Now the temperature difference is theta is equal to T minus TA. We need the time required to attain the temperature as 95 for the sphere. So to attain the temperature 95, we have to calculate the time. So theta is 95 minus 15, you get 80 degrees centigrade. And initial temperature difference is, initial temperature is 290, ambient temperature is 15, we will get the temperature difference as 275 degrees centigrade. So this is initial temperature difference. So you can use the equation theta by theta is equal to e raised to minus hat by rho VCP is equal to, taking the surface area to the denominator, you will get B by A, which is characteristic length. So you get the equation theta by theta I is equal to e raised to minus ht by rho LCP. Now substituting for theta and theta I, theta is 80 and theta is 275 is equal to E raised to H is 45 and the density is 2700. Characteristic length we already got it, substituting characteristic length, and Cp is 900 joules per kilogram Kelvin. Substituting and solving, we get the time as 383.59 seconds. So it requires 383.59 seconds to attain a temperature of 95 degrees centigrade. From an initial temperature 290 degrees centigrade to reach 95 degrees centigrade, it requires 383.59 seconds.